and welcome to our talk about Monorepo, one repo to rule them all. My name is Yael Green, and I work as a software team lead at Immubit. I develop mostly backend in Python, and I love technology and collaborating with other people. Just a few words about Immubit before we start. We deliver an AI process optimization solution for oil refineries and chemical plants. Our end-to-end solution is currently running in the world's largest refineries and petrochemical plants, unlocking millions of dollars a year in annual margin for our operators. So if you'd like to hear more about us, please feel free to reach out. We have a booth today here at PyCon, and we would love to talk to you. And in case you haven't noticed, we're hiring. So just before we dive into the agenda, let's start with what's in it for you. Does your service architecture slow you down instead of enabling rapid and frequent deliveries? If you have found yourself in this situation, you will benefit from hearing about our journey towards an efficient repository structure. At the end of this session, you will be able to choose the correct repository structure for your project, and you will gain practical tools to implement a monorepo and conduct a safe transfer. On our agenda for today, we will start with answering the question, why did we move to a monorepo? Next, we will discuss the correct repository structure for you. Then we will talk about Python specifics of a monorepo. And last, we will dive into our implementation of a monorepo. So, as I said, our first topic for today is answering the question, why did we move to a monorepo? We will discuss the many reasons we had to make this decision and how it improved our development. We had two main root causes. First, our microservices weren't so micro. In a classic microservice architecture, the services are fine-grained and loosely coupled. Together with lightweight protocols, this architecture is meant to support fast and easy development across teams by reducing dependencies. But in reality, our microservices were services. Each one had one big area of responsibility. They served multiple purposes and had a strict API. Second, our libraries were shared across too many services. Instead of serving a small, specific purpose, many of our libraries each had responsibility for a large area. This caused the services to be tightly coupled, since they were shared a few libraries. We also had one application database which all our services wrote to and read from. This too created a strict coupling between our components. Here is an illustration of what we had to deal with. Does it look familiar to anyone? These two main root causes led to the following issues. Cross-testing. A change to a library that was shared between more than one service required a developer to test the new code with all the dependent services. So, to overcome this, we added the dependent services test to the library testing pipeline. But this made the testing pipeline long and sometimes was still not helpful, since the development included changes in another library. So you're wondering, what did we do in this case? Well, we would test locally, mark the test as allow failure, we would push the change, and after it was merged, we would merge another change to revert back that allow failure to pass, and yes, it really was as ugly as it sounds. Multiple merge requests. Many features require development across multiple services and libraries. We had to open a merge request for each one and manage the review and merging separately. Another pain point was when a change to a library had to be shared between more than one service. That also required us to merge the new version into all the services' requirements. This took unnecessary extra time and also left our codebase in an inconsistent state. And in some cases, a developer discovered he accidentally caused a bug. Now he had to revert multiple merge requests, fix the bug, and start testing in the merging process all over again, leaving the codebase in a broken state until he was done. Deployment. A single deployment is composed of multiple components, and the components share libraries that must be aligned. To create a deployment, we had some complex logic to tag all the branches in the repository, push all the images to our PyPy, and maintain a list of all those tags and images, and pull them to bundle them together into a release. This was a lot of work to support multiple repositories, and in our case, it was specifically unnecessary because we rarely released a version that had changes in only one component. Unpleasant surprises. Although we added the dependent service tests to the library testing pipeline, we still merged bugs into our code base. It was complicated to be sure that we had fully tested our development. This could have happened if the development spun across multiple services and libraries and could not be tested in a single CI pipeline. Or this could have happened if the development changed a component that changed another component that broke another component that was dependent on it. Yeah, indeed unpleasant surprises. After examining our options, we decided that moving to a monorepo was the best way to solve many of our problems. Moving to a monorepo, we would achieve the following benefits. Simple testing. The single merge request will run all relevant tests in a single CI/CD testing pipeline. No more waiting for multiple dependent pipelines and no more surprises. Developers will have all the reassurance they need in one place. Single merge requests. Any new feature or bug fix can be executed with a single merge request that will hold all the changes in all services and in all libraries. This allows a fast and easy way to commit all changes to the master branch for multiple libraries and projects. Dependency management. Holding all our code in a single repository will allow us to align a library version, internal or external, across all services and libraries in the entire project. Sharing tools. The new structure also allows us to easily share tools and scripts across our entire code base. This was a bonus feature that we were happy to utilize. So now that I have shared with you all the reasons we moved to using a monorepo, and you know all about how it made our development faster and our testing and deployment much easier, I am sure you are running to move your code base into a single big and great monorepo as well. So before you do that, I want to take us to our second topic for today. How to choose the correct repository structure for you. There's no right or wrong repository structure. They both have pros and cons, and it's up to you to decide based on your needs. We will talk about the pros and cons of monorepo and multi-repo and give you all the information you need to make the right decision in your case. Let's start with the pros of a monorepo. Since all the code is shared for all developers, this structure supports collaboration of developers from different projects and teams. It also supports sharing of common best practices, tools, scripts, and definition across all the codebase and all contributors. Second, a monorepo also allows simple dependency management of internal and external libraries. Moving on to the monorepo cons. If your codebase is extremely large, you might have performance issues with it. So this is important to note, but I wouldn't worry too much. I guess if Google is using a monorepo, so can you. In monorepo, it is difficult to divide areas of responsibility. When developers from all teams are using the same repo and have the same permissions, it's not easy to draw the line between the team's responsibility over the different areas of the monorepo. Now that we have talked about monorepo, let's discuss the pros and cons of multi-repo. Starting with the pros. Using a multi-repo gives you better access control across the organization. Each team or group can have access to the repository based on their need to know. Which also brings us to our next point. It is much easier to divide areas of responsibility when your codebase is divided into repositories. And different repositories are visible to different teams based on their needs. Moving on to the cons of multi-repo. Using a multi-repo causes difficulties managing the dependencies across all repositories. Any library alignment must be handled explicitly. Another disadvantage is that it will be harder for developers to see the bigger picture. When the code they see is scoped, so is their understanding of the general architecture. And before we move on to our next topic, let's conclude that, as we saw, choosing a repository structure must be done based on your specific needs of your project. For our next topic, let's discuss some Python specifics of Monorepo. What is a recommended repository structure? Should we use relative imports? And why are editable installations so wonderful? One great yet tricky thing about Python is the freedom we have in some cases, such as repository structure. I will suggest a simple and straightforward structure. Divide all your repos into services and libraries. Place all the services and libraries under the correct folder. And in the root directory, place your repository CI/CD definition. We use Gitlab, so for us it was Gitlab CI YAML. And also place all your cross-repository tools and definition in the root directory. Next, here we see the structure of a single project. All services and libraries should follow the exact same structure. In the root folder, store your Docker file, if you have one, CI/CD definition, requirements. We use pip file, so our requirements definition is a pip file and pip file lock file, and the folder containing the code and the tests. The important part here is that each project defines its own CI and requirements in the exact same way. We will later see why this is so important and how it allows us to truly test our development. As you know, Python allows us to use relative imports. Look at it, it's so short and clean, and now that we put all our code in the same repository, it's so tempting to use. But I don't recommend using relative imports in your monorepo. First, it's generally bad practice in Python, and second, by doing it, you are creating a contract between your code and your repository structure, and it's a much better idea to keep them decoupled. Editable installations are absolutely one of the best perks of using a monorepo. Finally, we can get rid of pushing libraries to PyPy. Instead, we can simply install them from source. So simple, and we can always be sure that we're using the correct library version. Finally, we are ready for our last topic. In this section, we will deep dive into our implementation. We will discuss how we conducted the transfer and how we implemented our CI. To create a new monorepo composed of all multi-repos without losing history, we use the script called tomono from GitHub. This script merges multiple independent repositories into a single monorepo. Basically, every repo is moved into its own subdirectory and all branches are merged. On a small side note, in our case, we had to make some changes to the script to support our multi-repo. Just a small example, not all our master branches were named master, so we had to take care of that, and you may have also specific things you will need to take care of. So how does this generally work? Every repository is fetched and fully handled individually and sequentially. First, fetch all the data related to this repository. Next, immediately check out and initialize every single branch which belongs to that repository. Here we see the script for every repository. In blue, we fetch all the data related to the repository, and in green is the pseudo script that we will deep dive to in the next slide. For every branch, and this is where the real magic happens. Here we're in a constant context of a single repository checkout, and for each branch, we will independently check out into a subdirectory for that repository, This is what we see here in orange. And we will merge it into the Monorepo. That's what we see here in purple. Another aspect of our implementation is our CI. How did we run the correct tests for each branch and for each merge? The solution is divided into three main parts. First, we define the dependencies between our libraries and projects. Next, we created a project job template. And last, for each pipeline, we dynamically generated the job based on the dependency definition and the project job template. Starting with the first part, here we can see an example of a dependency definition. In this case, we have one service and one library. Under services, you can see service A. We have a key for its path, and its dependencies is one dependency libc. Under libraries, we see library C. We have its path saved in the path key and its dependencies. In this case, no dependencies. The second part is the project job template. As you can see here, the template will iterate over the projects, and for each project, it will define a job with the project name. This job is of type trigger, and it includes the GitLab CI file of that project with the strategy depend. The depend strategy defines that this job will pass only if the jobs included in the CI file will pass. So now, we have the dependencies defined in a config YAML file, and the template for creating jobs according to a list of projects it will receive as input. And now, all we need to do is to dynamically fill in that template. Here is our third and last part. To dynamically generate the job for our Monorepo, we defined a generate job. In this job, the before script will prepare the environment, install Git, create an artifacts folder, and install some Python packages. In the script itself, we will clone the relevant remote branch of the Monorepo, and in our local branch, we will run a Python script. This Python script will compare, using gitdiff, the remote branch and the local branch. Now we have a list of all the projects and libraries that we have changed in our branch. We will use the dependency definition from the first part to expand this list and add to it all the dependent libraries and projects. Now, we use the expanded list as input to our job template, and we generate a CI file with a job for each project, lib, and dependent project or lib. The next job is project's job. Here we include the CI file we generated in the previous job. And this concludes our solution for running the correct tests for each branch and for each merge. For further read, I encourage you to visit my post on Medium and my GitHub project with all the examples and the snippets from our session today. So just before we finish, I want to remind you that we are hiring, and you're welcome to visit the link of our careers on our page or come talk to us in our booth. Thank you all for joining our session about Monorepo, one repo to rule them all. Any questions? Yeah, that's a great question. I'll say that again. Probably not everyone heard. What's your name? Binyamin asked about virtual environments. So over here, what we recommend, but each developer can do whatever he wants, is that for each service, we will create a virtual environment for that service using the requirements of that service, because we lock the requirements for each service. And when we are testing locally or running some libraries, then we will use one of the services that are running that library. And then that way we know that we are testing it in the context of the service that it runs in it. But that's not something that we have defined. That's not something that every developer must do it exactly that way. Some developers also would like to create virtual environments also for each library. That could also be done, but it's actually not needed. It's easier to use the service that it runs inside.
The most confusing part for me when you have a shared code, like an external library, so it should be independent of any external libraries. Because if, for example, one service runs on Python 3.9 and one 3.10, so the library that we're using should be version agnostic.
Yeah, so I think that the answer for that is that sometimes we have libraries that we're using in our services that are internal libraries, and then we want to know that we're fixing the version for that library. So it's true that I would think that the answer to that is also that there's a difference if you're using external or internal libraries in what is your intention. So, any other questions? Yeah, what's your name? Kobe. So Kobe asked, what do we do in this situation if we have some specific library that we want to open source or to export? So how would we handle that? So we actually do have one repository that's not inside the Monorepo. And we're not because we're sharing it, but that's the case. And for that, we will fix the version inside the service that are using it. So if you intend to have a specific library that you want to export, then you should probably not put it in your Monorepo. But that's a nice point. So thank you.
You use different tools or modules?
We use an internal PyPy because it's internal, and I think I mentioned we use pip file to manage our requirements. Yeah. Okay, so thank you everyone, and enjoy the rest of your day.